Okay, now we're going to look at Newton's second law, but in 3D. It's basically this Newton's second law in 1D, except 3 times. Just so you know. All right. A soccer ball is kicked across the field by a player. It undergoes an acceleration. Now, to be clear, this is an initial acceleration because once he kicks it, it's no longer accelerating. Given by blah. Find the resultant force acting on the ball and the magnitude and direction of the resultant force. That's, oh, because that's the acceleration. I understand what's happening now. Okay, so we know that the sum of the forces, and I'm going to rewrite this, so A equals 3I plus 7j hat. So acceleration of the ball equals 3I hat plus 7j hat. Okay. So since I know the sum of the forces in the x direction of the ball, so if I draw a free body diagram of the ball, the kid is kicking it, but I can kind of, so like this is his foot, but I can resolve his footness into x and y components. So I'm going to make that a thinner so you can see it's just a component. So here's the x component, and I like to draw it here, although I guess technically it goes here. So whichever way makes the more sense for you. I just like seeing the triangle, but other people like seeing where it's applied, so it just kind of depends on whatever makes most sense to you. I think I'll leave it like that for now for clarity. So this is the, oops, not A. This is the x component of the foot force. I'm going to call it something besides F. Shoe. This is the x component of the shoe, and this is the y component of the shoe. And this is like shoe vector. Okay? So the x component of shoe vector, I don't know what it is, but I'm just going to label it random SX. So shoe vector in the x direction, force equals mass times acceleration. So it's going to be the mass of the ball times the acceleration of the ball in the x direction, which happens to be 3. So tell me the mass of the ball. 0.4 kilograms. Okay, so I can just, okay. So SX equals 0.4 times 0.3, and because this is where I'm going to get it wrong, so I'm going to put the decimal point in the wrong place. Yeah, 0.12. Okay, you can make fun of me for that later. So that means the x component of the force of the shoe on the ball is 0.12. Okay, now the sum of the forces in the y. Now here's the question. Do I include gravity? I don't know what it wants me to do. Because if it has an initial acceleration of that, normally I would put gravity, but I don't know if it wants me to. I'm going to cheat because, yeah, it doesn't want me to. It's not using gravity. So this isn't a gravitationalless, yeah, okay. We're assuming no gravity in this universe, which, fine. So let's add a very important statement here that says, I don't know, like ignore the immediate effects of gravity, or the kicking provides an acceleration of that. Maybe, okay, maybe I'm just reading too much into it. I overthink problems. If you overthought that problem, you and I can be friends. If you didn't overthink that problem, you and I need to be friends because you need to teach me how to read these problems better. So we're just looking at the force causing that acceleration. So I might have worded it like the force causes an initial acceleration of blah, 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 of the 3I hat plus 7j hat. Because I just think that makes a lot more sense. Okay, so anyway, the problem is easier that way anyway. So now it's the mass of the ball, which I know to be 0.4 times, you know what I did? After all that talk, I wrote times 3, and I wrote it as 0.3, and y'all were like, yeah, I know. See, I was going to make fun of you for that, but I'm just going to do this. 1.2. See, I still do it wrong because I was already thinking about the next step. This is where things go badly. Oh, what are the units on this? Newtons. 1.2 newtons. I was like, that's really small. So, because 7 times 0.4, and it's because I used parentheses instead of a times symbol. You may or may not have gotten to this point in your math career, by the way. See how my plus signs are like this, but my t's are like this? That's because I got a lot of problems wrong by thinking t's were plus signs and plus signs were t's. So, yeah, eventually you'll get to where, like, this is my lowercase u, this is my my lowercase v, but this is my uppercase v, and this is my uppercase u that has a chunk on it. Like, the struggle is real, man. S sub y is 2.8 newtons. Okay, so those are the two components. So the magnitude of that force is the square root of the sum of the squares. So the square root of the sum of the squares is the magnitude. And my brain is fully broken now because I'm super embarrassed by the fact that I can't do basic math. Plus 2.8 squared. And that's 3.05. So the magnitude of S is 3.05 newtons. Okay, so what were the questions? Find the resultant force and the magnitude and direction. Okay, so the resultant force, if I was going to write the force as a regular vector, force equals 1.2 I hat plus 2.8 j hat newtons. The magnitude is that. And if I kind of look at this triangle again, S could also be drawn down there. So I have S is 1.2. Here, I'm just going to redraw the triangle. It's not a very pretty triangle. 1.2 and 2, whoa, come back. 2.8. Theta is the inverse tangent of opposite over adjacent. I prefer not to just memorize because things can get weird if you don't always measure from the positive x-axis. So it's a good habit to get into just looking at it every time, and then you're not memorizing equations. You're actually understanding what's going on, which is always a plus. Okay, 66.8 degrees. Sort of, maybe, ish. Good enough. Yay, I got it right. I'm amazing. How many more of these are there? Holy mackerel. Okay. Newton's second law, momentum. Oh, I don't want to do momentum. Can I throw a hissy fit? I mean, if history has taught us anything. Find the mass of a car if a net force produces an acceleration. Okay, can we? Sure. Okay, find the mass of a car. So if we're doing the sum of the forces in the y direction, a net force of 600, so it's 600 down, produces an acceleration of negative 0.2. Well, I feel like I can do that. 600 divided by 0.2 is 3,000. And that's 3,000 kilograms. Oh, look at me. I'm kind of a genius. That's a scalar. All right, I did that one. I don't know why I cried so much about it. All right, some of the forces on a particle. Particle of mass is acted by 4 forces. Okay, now we're ready to party. Here's this particle. Particle! 4 forces of 4 magnitudes. Oh, with the directions. Like, how am I supposed to know what directions they are? Okay, they're apparently shown in the figure below. What is the acceleration of the particle? Ooh, hot damn. Okay, so 10 and then 40. Heaven forbid we label them on the picture. 10, 40, Oh, they even made them like kind of proportional to their size. That's cute. 5 and 2. Okay, so here we go. Now, all of these are already entirely x or entirely y, except for that stupid F1 thingy. So let's break out F1. So F1 is currently 10 newtons. Now, if you're good, you can immediately look at this and go, oh, well, if it's 30 degrees, then this side is 5 and this side is 5 square root of 3. And if you're like, huh, it's because you don't know your special triangles, and that's a whole other day for special triangles. In fact, that seems like a great thing to put in the review, special triangles. Okay, so we've got our special triangles here, but we could also have said this will be our F1 in the x, F1 in the y, and we could be like sine of 30 is F1 in the x opposite over hypotenuse. So F1x equals 10 times sine 30, which comes out to 5. And then cosine 30 is F1y adjacent over hypotenuse. So F1y is, I'll give you the actual answer, 10 times cosine 30, 5 square root of 3, or 8.66. And these are all newtons. So honestly, the next thing I would do on this problem is I would redraw it. And I honestly wouldn't redraw it to scale because that's just, that 40 is too long and it's driving me nuts. So I have 5 this way, I have 2 this way, I have 40 this way, and then from that 10, I've got 8, and I'll draw it in a different color just to make it clear what's happening. I have 8.66 this way, and then 5 this way again. Okay, so what was I actually trying to find? I've already forgotten, because that's how all word problems are. What is the acceleration of the particle? Okay, so I've got this dude here. Now I just break it out into x and y components. So I've got some of the forces in the x is 8 going forward minus 5 going backwards equals mass times acceleration in the x. And I already forgot what the mass was. I have to go look at it again. Come on, girl. 4. That's a disappointing. So 4. So 8.66, and I'm not using the rounded off version, minus 5 divided by 4. So acceleration in the x direction is, whoa, there we go. Acceleration in the x direction is 0.915. And because everything was in the correct units, kilograms, meters, and seconds, this is in meters per second squared. Then some of the forces in the y, okay, 2's going up, 5's going up, 40's going down, and that's equal mass times acceleration in the y direction. This one I'm going to be a little bit more careful. 2 plus 5 minus 40, so that's negative 33 equals 4ay. So ay is going to be negative 33 divided by 4, giving me negative 8.25. So it's actually going negative 8.2. Well, that makes sense because the 40 is so big. That's why it makes sense when you draw it to scale. So basically it's going to the left, sorry, to the right a little bit, but it's going down a lot. So this is like its force, its direction. It's going this way. This is acceleration vector. So the acceleration vector is 0.915 I hat minus 8.25 j hat meters per second squared. Is that what they got? Let's hope, because when I don't get the same answer they do, it's embarrassing. Okay, is that what I got? 892 and 83? I already forgot. 9, 2, and 8, 3. Yes, beautiful. And they got negatives? Maybe? Yes, okay, good. All right, so we got the same answer. And then they can also do directions by doing trig. Do this one. Okay, let me just set this one up for you. So it's just asking what is the net force on the car and what is the acceleration. I'm just going to let you know as soon as I see these problems, first thing I do, here's car, and then I break these out. So this one is 380, and whatever sign it's next to is the cosine, right? Because cosine is adjacent. So this one will be 3, actually let me use a thinner marker because I'm going to be writing a lot here. So this will be 380 cosine 10, and then the opposite, this dude, right, this is opposite from the 10 degrees. So this will be 380 sine 10 degrees. So that's this guy. And then this guy here, this guy here is 450. So he's 450, remember this is opposite. Opposite 450 is sine 30, and adjacent is cosine. So 450 cosine 30. So that's another reason you don't want to remember that, like, oh, cosine is always x. It's not always x. Cosine is always adjacent. And so that's why it's always really important to look at the picture, not memorize formulas, but really understand what's physically going on in the problem. So now that I have my forces broken out into the x and y directions, now I can be like, some of the forces in the x directions are, you know, this will be positive, this will be negative, and that equals mass times acceleration in the x. Some of the forces in the y direction, these are both positive, and that equals mass times acceleration in the y. So hopefully that'll be kind of enough to get you going. And whew, there's a lot of material here, but you got this.